In this lecture, we look at path diagrams for several common types of statistical models. Many of these models you will be familiar with, while others may be less familiar to you. The models range from very basic to quite complex, but regardless of the complexity, they can be represented using path diagrams, which helps make the models more understandable and interpretable. In doing this, we will see why many familiar statistical models can be considered to be special cases of the structural equation model. In addition, because SEM software can be used to fit models that can be represented using path diagrams, it will become clear that we can use SEM software to fit a wide variety of types of statistical models. Here's an outline of what we'll be looking at in this video. We're going to be looking at a number of common model types. We'll start off with some basic models and then progress to more complicated models. We'll look at the correlation model and then the univariate simple linear regression model. We'll then look at the univariate multiple linear regression model. We'll then look at the multivariate multiple linear regression model. We'll then look at the exploratory factor analysis model, a mediation model, and finally a reciprocal causation model. Now for each of these models, we will represent the model using a path diagram, as well as a system of one or more statistical equations. Also, for each type of model, we'll identify various inferences of interest, such as hypothesis tests and confidence interval estimation, that would be germane in the context of that kind of a model. So let's jump in. So we'll first look at the correlation model. And so here is a path diagram for a correlation model. We have two response variables, y1 and y2. These are manifest variables because they are contained in square boxes. Now recall that a two-way arrow indicates a correlative relationship. And so in this model, we can see that we are going to be modeling the correlation between y1 and y2. And that correlation is denoted by lowercase rho. In addition, we have an asterisk on rho, and so that also indicates to us that that is an unknown parameter that needs to be estimated. Here is a representation of this model using statistical notation. So we let y1 and y2 be jointly distributed random variables. The correlation of y1 and y2 is equal to the ratio of their covariance to the square root of the product of their variances. So rho, which is the correlation of y1 and y2, is equal to the covariance of y1 and y2 divided by the square root of the product of the variance of y1 with the variance of y2. And you'll recall that the covariance of two random variables is equal to the expected value of the product of the difference of each random variable and its expectation. So the covariance of y1 and y2 is equal to the expected value of the product of y1 minus its expected value and y2 and its expected value. Again, there is one parameter to be estimated in this model, which is rho, the correlation coefficient. And the typical types of hypotheses that are of interest when doing a correlation analysis would be these kinds of hypotheses. So for example, a two-tailed test, where the null hypothesis says that the correlation coefficient is equal to some pre-specified value, rho 0, versus the alternative, which says that rho is not equal to that constant. A left-tailed test, where the null hypothesis says that rho is greater than or equal to some pre-specified value, rho 0, versus the alternative, which says that rho is strictly less than that value. And finally, a right-tailed test, where the null hypothesis says that rho is less than or equal to some pre-specified value versus the alternative, which says that rho is greater than that value. Now, in many cases, when we're doing a correlation analysis, the hypothesized value, rho 0, is 0 itself. And so we would ask the question, are these two random variables correlated or not? And so if we were to test the two-tailed test, perform the two-tailed test, and reject that null hypothesis, we would be able to conclude at a given level of significance that the two random variables are correlated, that they have a non-zero correlation. In some situations, we may want to try to show that the correlation is less than a particular value, and in other situations, it may be meaningful in a given context to try to show that the correlation is greater than some value. So oftentimes, rho sub 0 will be 0 in these hypothesis tests, but not always. All right? It depends on the context. Now, in addition to testing hypotheses about the correlation coefficient, where we are making qualitative assessments, qualitative decisions about the value of the correlation, we can also construct confidence interval estimates for the correlation coefficient. And we would typically follow up any kind of a hypothesis test with a corresponding type of confidence interval. And so, for example, we could construct a lower confidence limit for a correlation coefficient. We could construct an upper confidence limit for that correlation coefficient. And we could also construct a two-sided confidence interval for the correlation coefficient. Next, let's look at the univariate simple linear regression model. Consider a univariate simple linear regression model involving a response variable y and an explanatory variable x. Here's the path diagram for this model. You'll notice that both x and y are manifest variables as indicated by being contained in squares or rectangles in the path diagram. In addition, recall that one-way arrows indicate a one-way predictive regression type of relationship. And so we see here that we have a one-way arrow going from x to y. And so this tells us that x is predictive of y, or x impacts y. We also have a one-way arrow going from the error term epsilon to y. And then finally, we have, perhaps this is a new notation for our path diagrams, but we have a one-way arrow going from the digit 1 to the response variable y. And that allows us to include the intercept in the model. And so you'll notice that the coefficient on that particular arrow is beta 0. All right, and so that allows us to include beta 0 in the model as a intercept. The coefficient on the path from x to y is beta 1, and so that is the slope coefficient, which is multiplied against x in that model for the response variable y. Now here is the representation of this model as a statistical equation. And so we see here that we have y equal to beta 0 times 1 plus beta 1 times x plus epsilon. And we can simplify that to the more traditional way of writing this as beta 0 plus beta 1 times x plus epsilon, where the error term epsilon is typically assumed to be normally distributed. And by convention, the mean of that error distribution is 0. And we denote the variance, which is unknown, to be sigma squared. Now we can also express this model for individual subjects. And so the model notation for n individual subjects is obtained by subscripting the response and explanatory variables as well as the error term as follows. So I'm going to use the subscript I in this case to identify different individuals. And so for the ith individual, we would have the regression equation y sub I equal to beta 0 plus beta 1 times x sub I 1 plus epsilon sub I. So each individual has its own response variable, y sub I, its own value for the explanatory variable, x sub I 1, and epsilon sub I. Here I goes from 1 to n for the n subjects. And then we would also subscript the error term with I. And so each of those error terms is assumed to be normally distributed, typically. Again, by convention, with a mean of 0, and the variance of that error distribution is assumed or is denoted by sigma squared. In addition, the model error terms are assumed to be stochastically independent. Now, in this model, there are 3 parameters to be estimated, as indicated by the 3 asterisks in that path diagram. Beta 0, the y-intercept of the model, beta 1, the slope coefficient on x, and sigma squared, the variance of the error term epsilon. Now, some common types of inferences that are of interest when we're doing simple linear regression, perhaps the most important is to first test to see if there is a linear relationship between the response variable and the explanatory variable. All right, and so we could do this by testing hypotheses about beta 1. In general, we have 3 kinds of tests that we can perform: a two-tailed test, a left-tailed test, and a right-tailed test. In the two-tailed test, the null hypothesis says that beta 1 is equal to some specified value, beta 1 star. The alternative would be the opposite of that, so the slope coefficient beta 1 is not equal to beta 1 star. And by the way, my use of asterisks here is different than it is in path diagrams. Here I'm using the asterisk to indicate or to denote that this beta 1 star is some specified value that we would have in the context of a real problem. All right, then we have the left-tailed test, where we're trying to show that beta 1 is less than some particular value, beta 1 star. And so the null hypothesis would be that beta 1 is greater than or equal to beta 1 star, and we would let the data try to convince us otherwise. In other words, that beta 1 is less than beta 1 star. And finally, if it were important in the context of a particular problem to try to show that beta 1 was greater than some value, beta 1 star, we would perform a right-tailed test. And so the null hypothesis would be that beta 1 is no more than beta 1 star, and then we would let the data try to convince us otherwise. In other words, that beta 1 is greater than beta 1 star. Now, in many situations, in particular, if we are trying to determine whether a linear relationship exists between the response variable and the explanatory variable, then beta 1 star, the hypothesized value of beta 1, would be 0 in these hypotheses. But there are many situations where non-zero values of beta 1 star would be important to test. Now, in addition to testing hypotheses about the slope coefficient beta 1, we always want to construct confidence intervals of some type for that slope coefficient as well. So in addition to making qualitative assessments, qualitative decisions about the slope coefficient, we also want to get an idea of the value of that slope coefficient. And we can augment the point estimate that we get when we fit the model by constructing a confidence interval of some type. In some situations, A lower confidence limit for beta 1 would be all that we would need. In other situations, an upper confidence limit would be appropriate. And in many situations, a two-sided confidence interval for the slope coefficient beta 1 would be appropriate. Next, let's step up the complexity just a little bit and look at a univariate multiple linear regression model. And so you'll recall that a multiple regression model is a regression model that has more than one explanatory variable. And so consider a univariate multiple regression model involving one response variable, which we will denote by y, and three explanatory variables, which we will denote by x1, x2, and x3. So here we have a path diagram for this univariate multiple linear regression model with three explanatory variables, x1, x2, and x3. Now recall that a one-way arrow indicates that we're looking at a one-way predictive regression type of relationship. And so we have our explanatory variables, x1, x2, and x3, which are in squares, and so that tells us that these are considered to be manifest variables, observable variables. And each of those explanatory variables has emanating from it a one-way arrow to the response variable y, which is also enclosed in a square, and so that tells us that the response variable y is also considered to be a manifest variable. And so we have these one-way predictive regression type of relationships relating each of the explanatory variables, x1, x2, and x3, to y. And so x1 is allowed to impact y, x2 is allowed to impact y, and x3 is also allowed to impact y in this model. In addition, we have you can see this notation here, we have the 1 with a one-way arrow going towards the response variable, and the coefficient on that arrow is beta 0, and so that allows us to include an intercept in the model. And then finally, we have the error term epsilon with a one-way arrow starting at epsilon and terminating at y. And so we see here that y is not allowed to impact x1, nor x2, nor x3, nor epsilon in this model. All of these other terms are impacting the response variable y. Notice also that we have 5 asterisks in this model, asterisks on beta 1, beta 2, beta 3, beta 0, and then on epsilon. And the asterisk on epsilon corresponds to the variance of that error term. And so that tells us visually by looking at the diagram that we have 5 parameters in this model that will need to be estimated. Here is a representation of this model as a single statistical equation. And so the corresponding univariate multiple linear regression model for this situation is expressed as a statistical equation in the following way. So y equal to beta 0 plus beta 1 times x1 plus beta 2 times x2 plus beta 3 times x3 plus the error term, where the error term is typically assumed to be normally distributed. By convention, the variance of the mean of that error distribution is taken to be 0, and we denote the variance of the error distribution by sigma squared. Now, this univariate multiple regression model can also be represented in matrix form for an individual subject or experimental unit in the following way. And so we have the vector bold y equal to the matrix, in this case it's a row vector bold x, times the column vector beta, which is the 4 by 1 vector containing the parameters beta 0, beta 1, beta 2, and beta 3. The x vector, which is a row vector, contains the quantities 1, x, x2, and x3. And then finally, bold E is a 1-by-1 matrix containing the error term epsilon. So we could represent this statistical equation that is written using the individual coefficients and variables. As it is on this slide, we could write this in matrix form in this way. Now, why might we want to do that? Well, let's look at the model notation for the individual subjects. And so let's suppose that we have n individual subjects or experimental units that we have data on. And so the model notation for n individual subjects is obtained by subscripting the variables, the response variable and the 3 explanatory variables, as well as the error term as follows. And I'm going to use I as my subscript. And so y sub I equal to beta 0 plus beta 1 times x sub I 1 plus beta 2 times x sub I 2 plus beta 3 times x sub I 3 plus epsilon sub I. And this is for I going from 1 to n. So each subject has its own value of y and its own values for x1, x2, and x3. And in addition, the typical assumption is that the error terms are normally distributed by convention with a mean of 0. And again, we denote the variance of the error distribution by sigma squared. And the other assumption is that the model error terms across the various subjects are stochastically independent. Now, with this notation and the notation in matrix form on the previous slide, we can very easily construct the matrix representation for data from all subjects. The matrix form of the model for the combined data is of the form y equal to x times beta plus e, where in this case, y is equal to the n-by-1 vector containing the response variables for the n subjects, y1, y2, and so forth down to y sub n. The X matrix is an n-by-4 matrix containing a column of 1s at the beginning that will be multiplied against beta 0, the intercept coefficient in the parameter vector. And then columns 2, 3, and 4 have the individual values for the explanatory variables for each individual subject. Now the beta vector stays the same because that is common across all subjects. And then finally the error vector, cap E, has the error terms E1, E2, and so forth down to E sub n. Now there are 5 parameters to be estimated, as was indicated in the path diagram. So beta 0, the y-intercept of the model. Beta 1, the slope coefficient on x1. Beta 2, the slope coefficient on x2. Beta 3, the slope coefficient on x3. And then finally, sigma squared, the variance of the error term epsilon. Now, there are a number of inference procedures or types of inferences that we may want to make about a univariate multiple linear regression model. In particular, we would want to test hypotheses about the various slope coefficients, so beta 1, beta 2, and beta 3 in particular. And so we could perform a two-tailed test, a left-tailed test, and or a right-tailed test for each of the 3 slope coefficients. Again, where b sub I star is some hypothesized value of beta sub I. Now, in testing the significance of each variable individually, special interest would be on the hypothesized values beta I star equal to 0. And so we would be able to determine, using, for example, a two-tailed test where the hypothesized value is 0, we would be able to test whether each explanatory variable is linearly related to the response variable y. And so those would be typically be of interest in any kind of a regression analysis, but in many situations, non-zero values of this hypothesized parameter value would be of interest in many situations. And in addition to two-tailed test, it may be relevant to test either a left-tailed test or a right-tailed test. And as always, in addition to performing hypothesis tests about the slope coefficients, beta 1, beta 2, and beta 3, we would also typically want to construct some kind of a confidence interval for each of those slope coefficients. Now, in some situations, we may also want to test hypotheses about the model intercept beta 0. And so, for example, we could perform a two-tailed test, a left-tailed test, or a right-tailed test, whatever is relevant in a given situation. And again, beta 0 star here is a hypothesized value of beta 0. In some cases, the hypothesized value may be 0, but when testing hypotheses about the intercept, that's not as common. In general, hypothesis tests about the intercept are not as common as a hypothesis test about the slopes, but in some situations they are relevant. And then finally, we could also construct some type of confidence interval for the intercept, if that would be relevant in a given situation. Next, let's generalize even further and look at a multivariate multiple linear regression model. Consider a multivariate multiple linear regression model involving, in this case, two response variables, y1 and y2, and three explanatory variables, x1, x2, and x3. Here is a path diagram for this multivariate multiple linear regression model. We see here that all of the variables, the explanatory variables x1, x2, and x3, as well as the two response variables y1 and y2, are all encased in squares. And so that tells us that all of these variables, all of the explanatory variables, and all of the response variables in the model are considered to be manifest or observable variables. And recall that one-way arrows indicate a one-way predictive regression type of relationship. And so we see here that we have one-way arrows coming out of each of the explanatory variables x1, x2, and x3 to each of the response variables y1 and y2. In addition, we have an arrow coming from the 1 symbol into y1, and the coefficient associated with that path is beta 0,1, and so that corresponds to the intercept for the model involving response y1. Similarly, we have a path going from a 1 symbol to the response variable y2 with the coefficient of beta 0,2, and so that is the intercept for the model associated with y2. We also have one-way arrows coming from the error terms into the response variables, and so epsilon 1 has a one-way arrow emanating from that error term to y1, and so that error term, epsilon 1, is impacting the response variable y1, and the error term epsilon 2 is impacting response variable y2 because there is a one-way arrow emanating from it to y2. Now notice that there are no arrows emanating from either y1 or y2. y1 and y2 only have incoming arrows. And so y1 and y2 in this model are not allowed to impact any of the other variables, and they're not allowed to impact each other. Now, notice also that we have a two-sided arrow connecting the two error terms, epsilon 1 and epsilon 2. And so that tells us that in this model, the two error terms are allowed to be correlated. The model is not forcing those two error terms to be uncorrelated. Finally, notice that we have 11 asterisks in this path diagram, and that tells us that we have 11 parameters that need to be estimated in this model. Here is a representation of this multivariate multiple linear regression model as a system of statistical equations. And so the corresponding multivariate multiple linear regression model is expressed as a system of two statistical equations in the following way. So response variable 1, y1, equal to beta 01 plus beta 11 times x1 plus beta 21 times x2 plus beta 31 times x3 plus epsilon 1. The second response variable, y2, is equal to beta 02 plus beta 12 times x1 plus beta 22 times x2 plus beta 32 times x3 plus error term epsilon 2. And we assume here that the two error terms are normally distributed. The variances of those error distributions are denoted by sigma 1 squared and sigma 2 squared respectively. And by the way, notice that we're not forcing in this model those variances to be equal. We're allowing them to be different. In addition, this model does not force the correlation between those error terms to be 0. And that's because we had that two-way arrow between or connecting the error terms. Now, in addition, the explanatory variables, x1, x2, and x3, are either taken to be measured without error, or the analysis is being done conditional on their observed values. And we know this from the path diagram because there were no two-way arrows connecting the x's. And in addition, we didn't have any asterisks for variances and things like that. And this is standard for a linear regression model. Typical or standard linear regression models again are done, or they're done assuming that the explanatory variables are measured without error, or the analysis is done conditional on their observed values. Now, this multivariate multiple regression model can also be represented in matrix form for an individual subject or experimental unit in the following way. Bold y equal to x times beta plus e, where bold y is a 1/2 row vector containing the two responses for an individual. Bold x is a 1/4 row vector containing a 1 in the first column, and then x1, x2, and x3, the three explanatory variables for that subject, in columns 2, 3, and 4. Beta is a 4/2 vector containing the parameters, the beta parameters for the two regression equations. And bold E is a 1/2 row vector containing the two error terms in that model. Model notation for n individual subjects is obtained by subscripting the variables, the response variables and the explanatory variables, as well as the error terms as follows. And so we're going to take the previous two regression equations and use I to subscript for each individual. And so we have for the first response variable, the equation for the ith subject would be y sub I1 equal to beta 0, 1 plus beta 1, 1 times x sub I1 plus beta 2, 1 times x sub I2 plus beta 3, 1 times x I3 plus the first error term for the ith subject, epsilon I1. For the second equation, for the ith subject, we have y sub I2 equal to beta 0, 2, the intercept for that second equation, plus beta 1, 2 times x sub I1 plus beta 2, 2 times x sub I2 plus beta 3, 2 times x sub I3 plus epsilon I2, the second error term for that ith subject. And again, the subscript I goes from 1 to n, where n is the number of subjects. The two error terms are assumed to be normally distributed. They are allowed to be correlated. However, error terms for different subjects are assumed to be stochastically independent. And then finally, again, the explanatory variables x1, x2, and x3, which in the notation on this slide have subscripts for the ith subject, are taken to be either measured without error or the analysis is done conditional on their observed values. Now, taking this notation along with the matrix representation on the previous slide, we can very easily come up with the matrix representation for data from all the subjects. And so the matrix form of the model for the combined data still has the same form as it had a couple slides ago, bold y equal to bold x times beta plus e. But in this case, bold y is the n by 2 matrix containing the row response vectors for the n subjects. The design matrix or regressor matrix, bold x, is the n by 4 matrix containing a column of 1s that will pick off the intercepts. And then the rest correspond to the values of the explanatory variables for each of the I subjects. The beta vector stays the same. It's still a 4 by 2 vector of beta parameters from the model. And then the matrix E is the n by 2 matrix where each row has the two error terms for a given subject. And so we can see that the way that we get these various data matrices is we build the data and error matrices by stacking the row data vectors in a vertical fashion. Now, like we said, based on the path diagram, we identified 11 different parameters that need to be estimated in fitting the model. And so we have beta 0j, the two y-intercepts for the equation for the jth response, j going from 1 to 2. We have two slope coefficients on x1, one for each of the two response equations. We have two slope coefficients on x2, one for each of the two responses, y1 and y2. We have two slope coefficients on x3, beta 3, 1 for the equation for y1 and beta 3, 2 for the equation for y2. We have the two error variances, sigma 1 squared and sigma 2 squared. And then finally we have the covariance between the two error terms, epsilon 1 and epsilon 2. And so that gives us 11 parameters to be estimated. Now, in terms of inferences about the various parameters, we typically want to test hypotheses about the model slope coefficients. And so hypothesis test about each slope coefficient, beta ij, where I goes from 1 to 3. So these are the coefficients on the x's. And then for each response variable, j going from 1 to 2. And so as usual, we could do a two-tailed test. We could do a left-tailed test. We could do a right-tailed test for any or all of these slope coefficients. Again, we have 6 slope coefficients in this multivariate multiple linear regression model. Again, beta sub ij star is a hypothesized value of beta sub ij that is meaningful in a given situation. And in testing the overall significance of the variables, we would certainly test the hypotheses that each of the beta ij's is equal to 0 against the alternative that they are non-zero. We could also test more specific hypotheses where we use non-zero values for the hypothesized value. And that would depend on the context and the application of the model. In addition, we could construct confidence interval estimates for the various slope coefficients. And so we could construct a lower confidence limit for the slope coefficients. We could construct upper confidence limits alone, or we could construct two-sided confidence intervals for the slope coefficients. In addition, although it's less common to do so, we could still test hypotheses about the two model intercepts. And so, again, whether we chose to do that, and if so, the values of the hypothesized values that we would use would depend on the application and the purpose for the model. And we could also construct some type of confidence interval for the intercepts if needed. Next, let's look at what's called an exploratory factor analysis model. And so here is the path diagram for an example exploratory factor analysis model. Now, the first thing I want to point out is that in this path diagram, we have two ovals or circles. And you'll recall that ovals or circles are used to represent latent constructs or factors, unobservable constructs in a path diagram. And so we have two ovals, and so we have two latent constructs or two factors in this model. In addition, we have 5 squares containing variable names z1 through z5, and those variables are manifest variables because, again, they are enclosed in squares. Now note that both factors are allowed to impact all of the manifest variables or indicators because emanating from each of the factors, from each of the ovals, we have one-way arrows going to all 5 of the manifest variables. Now, this is different from a confirmatory factor analysis model, where a given manifest variable is assumed to be an indicator for only one factor. In this particular model, each factor is allowed to impact each of the 5 manifest variables or indicators, and so all 5 manifest variables are allowed to be indicators of both factors in this model. And that is very, very different than a confirmatory factor analysis model. Now, note also that there is no two-way arrow connecting the factors. Now, because there's no two-way arrow connecting F1 and F2, this model is imposing the assumption that the factors are uncorrelated. And so it's going to impose that on the model fitting process. Now, this too is different from a confirmatory factor analysis model, because in a general confirmatory factor analysis model, the factors are allowed to be correlated. In the example of a confirmatory factor analysis model that we've seen, we had two-way arrows between each pair of factors. And that's in general what is allowed in a confirmatory factor analysis model. Now, a particular hypothesis, a particular research question to be checked may impose a constraint of zero correlation between factors, but the confirmatory factor analysis model itself, in general, allows non-zero correlations between factors. Now, this path diagram can be translated into a system of statistical equations. And so here are the equations for this particular exploratory factor analysis model. And so Z1 is equal to lambda 11 times F1 plus lambda 12 times F2 plus eta 1. Z2 is equal to lambda 21 times F1 plus lambda 22 times F2 plus eta 2. Z3 is equal to lambda 31 times F1 plus lambda 32 times F2 plus eta 3. Z4 is equal to lambda 41 times F1 plus lambda 42 times F2 plus eta 4. And finally, the fifth manifest variable, Z5, is equal to lambda 51 times F1 plus lambda 52 times F2 plus eta 5. In this system of statistical equations, the manifest variables Z1 through Z5 are standardized response variables. This is typical or standard in exploratory factor analysis. F1 and F2, as we've said, are unobservable latent constructs, and in the context of exploratory factor analysis, they are called common factors. The lambda ij's are unknown constants, and again, in the context of exploratory factor analysis, they are called factor loadings, and they're called that in confirmatory factor analysis as well. And finally, eta 1, eta 2, and so forth up to eta 5 are unobservable random error terms, and in the context of exploratory factor analysis, those are called specific factors. So we have common factors, the latent constructs, whose effects we're trying to identify using indicators. And then we have the random error terms, eta 1 through eta 5. Now note that the only observable quantity in each equation is the left-hand side, the manifest variables Z1 through Z5. Everything on the right-hand side of every equation is either an unknown constant that needs to be estimated, an unobservable latent construct, or an unobservable error term. Here are some additional assumptions that are indicated by the path diagram. And so the first is that the error terms, the eta values, are assumed to be uncorrelated, and the model is going to force that assumption or impose that assumption when it fits the model. In addition, the covariance between f sub I and eta sub j is 0 for all ij. In other words, the common factors and the random error terms, that is the specific factors, are again assumed to be uncorrelated, and that assumption is imposed in the model fitting process. Finally, the covariance of F1 and F2 is equal to 0 this is an assumption that is imposed, or it's specified by the lack of a two-way arrow in that path diagram, and so that's going to be imposed. And so in words, the common factors, F1 and F2, are assumed to be uncorrelated. And again, this assumption is imposed on the initial factor analytic solution. And so let me just say, we're not going to go into really any detail on this, but when you're doing an exploratory factor analysis, you come up with what is called an initial factor solution. And that solution has actually an infinite number of solutions. Now, in order to provide the best type of interpretability of the factors, what one does is what's called a rotation to try to get loadings that are as close to the poles -1 and 1 or 0 as possible. And there are two broad categories of rotation types: oblique rotations and orthogonal rotations. So the initial factor analytic solution is obtained in such a way that the factors are uncorrelated. But if you do an oblique rotation to get your final solution, then that method does allow for the factors to have a non-zero correlation in that final factor analytic solution. On the other hand, the other type of rotation method is called an orthogonal or rigid rotation method. And so what that's going to do is it's going to take that initial solution where the factors are uncorrelated, it's going to perform a rigid or orthogonal rotation. And because the rotation is orthogonal, it preserves that zero correlation between the factors. And so even in the final solution, if an orthogonal rotation method is used, the factors will be uncorrelated. Now, this system of statistical equations representing this exploratory factor analysis is often represented as a matrix equation. And so we have a z vector equal to a matrix denoted by cap lambda times F plus E, where the z vector is a 5x1 vector containing the standardized manifest variables. The lambda matrix is in this case, a 5x2 vector containing the lambdas in the model. Bold F is a 2x1, in this case, vector containing the two factors or latent constructs. And then bold E is a 5x1 vector containing the specific factors, or in other words, the error terms, eta 1 through eta 5. So this is how one could represent that system of equations using a matrix equation. And then from that system, the following matrix equation can be obtained. So we have P sub z equal to bold lambda times bold lambda prime, or transpose, plus cap psi. And in this matrix equation, P sub z is the correlation matrix of the vector of standardized manifest variables cap z. Again, bold lambda is the matrix of loadings, the matrix of the lambda values. And cap psi is the covariance matrix of the vector of error terms. In other words, it's the vector of the covariance matrix of bold E, and its structure is that of a diagonal matrix with the variances of the error terms, eta 1 through eta 5, on the diagonal. Now, this equation is very important. It's fundamental in the context of exploratory factor analysis. This matrix is called the factor analysis equations, and the initial factor analysis solution is obtained by solving this matrix equation for the loading matrix, bold lambda. Now, in this model, there are 15 parameters to be estimated. Lambda I1, I going from 1 to 5. So the loading of manifest variable I on factor 1. And so we have 5 parameters there. We also have lambda I2, I going from 1 to 5. The loading of manifest variable I on factor 2. And so that gives us 5 more parameters. And then finally, we have sigma squared sub I going from 1 to 5, where sigma squared sub I is the variance of error term eta sub I. And so that gives us 5 more parameters. And so we have 15 parameters total to be estimated. Now let's talk a few minutes here about the goals of exploratory factor analysis. So this particular model is presented with 2 factors just as an example, but in general, if one is doing an exploratory factor analysis, one of the initial and one of the primary goals of doing an exploratory factor analysis is to determine how many factors you actually have. How many latent constructs? And again, these are things that can't be measured. They cannot be observed directly, right? And so it's not clear how many factors exist. So how many factors, how many latent constructs are impacting a given set of manifest variables? So that's really the first thing that one needs to do when doing an exploratory factor analysis, is to determine in some way the number of factors that you believe are impacting the manifest variables that you have measured. Now, in the expression for the ith response variable z sub I, which again is lambda I1 times F1 plus lambda I2 times F2 plus eta sub I, in that expression, z sub I is a linear combination of 3 random variables, F1, F2, and eta sub I, and so it is itself a random variable. Now notice that the closer a factor loading lambda sub ij is to 0, the less of an effect factor j will tend to have on the random variable z sub I. The greater, in absolute value, the factor loading lambda sub ij, the greater the effect factor f sub j will tend to have on the random variable z sub I. And so this is important to keep in mind and to consider because this is going to help us to try to interpret what the factors represent. Now, once the number of underlying factors has been determined, the researcher tries to determine which factors are impacting which manifest variables. Or equivalently, the researcher tries to determine which manifest variables are indicators of which factors. Now, cutoff values are used for this purpose. And a common cutoff value of an absolute value of a loading being greater than or equal to 0.3 is often used, and that's, for example, the default in SAS, although there is no hard and fast rule for the cutoff value to be used. And in all factor analysis programs, there is an option to change what that cutoff or threshold is. Now, researchers want each manifest variable to be an indicator of only one factor. And so they will typically reject a manifest variable as an indicator if it loads heavily on more than one factor. Researchers use the indicators to interpret what each latent construct represents, and they do this based on the magnitudes and the signs of the indicators on which they load. So they try to determine which factors certain indicators are loading on, and then they use the magnitudes and signs of those indicators to interpret the factors on which they load. Once a researcher is satisfied with the number of factors, the indicators for each factor, and the interpretation of each factor, the exploratory aspect of the factor analysis concludes. Once the exploratory aspect of the factor analysis has concluded, researcher focus transitions from exploratory to confirmatory factor analysis. Now, although data are used in the development of factor analytic models, the structure of factor analytic models are driven more by theory in the particular field of interest than by data analysis and model fitting alone. Having said that, exploratory factor analysis and the development and perhaps updating of an underlying theory lead to a more refined theory, which is represented as a more refined model or path diagram, which can then be formally tested using confirmatory factor analysis. The next slide shows an example of a confirmatory factor analysis model for a refinement of the initial exploratory factor analysis model that we've been looking at. And so here we have two factors, F1 and F2. And notice that in this more refined model, Z1, Z2, and Z3 are indicators of F1, Z4 and Z5 are indicators of F2, F1 is not allowed to impact Z4 and Z5, F2 is not allowed to impact Z1, Z2, and Z3. And again, when we talk about impact in this kind of a context, we're talking about directly impacting, okay? Now, notice also that in this model, we have a two-sided arrow between F1 and F2. And so in this more refined model, we are allowing the factors to be correlated. And so again, note that each factor is allowed to impact only some manifest variables or indicators, and no manifest variable is an indicator for more than one factor. And this is what people doing factor analysis what they want. They want a limited number of factors for or indicators for each factor, and they don't want a particular indicator or a particular manifest variable being an indicator for more than one factor. So this is more refined than the exploratory factor analysis model that we looked at, which allowed each factor to impact every manifest variable directly and each manifest variable to be an indicator for all of the factors. And then finally, note also that the factors are allowed to be correlated. So once we get to the confirmatory factor analysis stage, we can then start formally testing hypotheses. And again, this is the purpose that researchers have in performing factor analysis. They start off with an exploratory factor analysis in order to identify the number of factors that underlie a given set of manifest variables. They then try to determine which manifest variables are indicators for which factor. All right, and if they have any manifest variables that are loading on more than one factor, they would typically either refine the measurement, refine the question, or get rid of it altogether so that they have a factor structure where each factor has a limited number of indicators, and each indicator is, or each manifest variable is an indicator of only one factor. And then once we have that, if we think about this particular diagram here, then some hypotheses of interest might be For example, hypothesis test involving the loadings on F1. And so the null hypothesis here would be that all three of those loadings are equal against the alternative, and this is shorthand notation here for differences exist among the three loadings. We could also test something like that with regard to the loadings on F2. In this case, the null hypothesis would be that the two loadings are equal in value against the alternative that they're different. We could also construct confidence intervals for the individual loadings. So a lower confidence limit for a particular loading, an upper confidence limit, or a two-sided confidence interval for a particular loading. It may be of interest to construct a confidence interval estimate of the difference between pairs of loadings, and we could do that via a lower confidence limit alone, an upper confidence limit alone, or via a two-sided confidence interval. And perhaps the most general type of thing we could do in terms of confidence interval estimation in this context would be to construct some type of confidence interval for some linear combination of the loadings. And so you can see the expression here that we have, the very general expression for a linear combination of the 5 loadings. And we could construct a lower confidence limit for that linear combination, an upper confidence limit, or a two-sided confidence interval. Next, let's look at what are called mediation models. And so here is a path diagram for a what's called a partial mediation model. Notice first that we have 3 variables, 3 response variables, y1, y2, and y3. They're each enclosed in squares, and so that tells us that each of these variables is a manifest variable, an observable variable. We have a number of one-way arrows. We have a one-way arrow going from y1 to y3. We have a one-way arrow going from y1 to y2. We have a one-way arrow starting at y2 and ending at y3. We have one-way arrows going from error terms epsilon 2 and epsilon 3 to y2 and y3 respectively. And then finally we have one-way arrows going from the digit 1 to each of y2 and y3 respectively. And again, that is allowing us to include intercepts in the models for those response variables. Now in this model, y1 is a predictor or explanatory variable, y3 is a response, and the variable y2 is what is called a mediator that affects the impact of the predictor y1 on the response y3. And so taking another look at our path diagram, y1 is a predictor, y3 is the response variable of interest, and y2 is what is called the mediator. The impact of y1 is being mediated by the variable y2. So in this model, y1 impacts y3 directly, but it also impacts y3 indirectly through the variable, through the mediator y2. Now here is a representation of this model as a system of statistical equations. This mediation model is expressed as a system of 2 statistical equations in the following way. y2, which is the mediator, is equal to beta 20, the intercept for this model, plus beta 21 times y1, the predictor, plus epsilon 2. y3, the response variable, is equal to beta 30, the intercept for that model, plus beta 3 1 times y1, where again y1 is the predictor variable, plus beta 3 2 times y2, where y2 is the mediator, plus epsilon 3. Now in this model, epsilon 2 and epsilon 3 are random error terms assumed to be normally distributed with a mean of 0 and with variances sigma 2 squared and sigma 3 squared respectively. And in this model, they are allowed to be correlated. Now here is a model that is called a complete mediation model. And so we see here that we have our predictor, y1, we have our response, y3, and we have our mediator, y2. In this model, however, y1 impacts y3 only indirectly through y2. And so because y1 can impact y3 only indirectly through y2, through the mediator y2, we don't have a direct path from y1 to y3. This is called a perfect mediation model or a complete mediation model. Now, this mediation model, this complete mediation model, is expressed as a system of statistical equations in the following way. So the mediator, y2, is equal to beta 2 0 plus beta 2 1 times y1 plus epsilon 2. y3, the response variable, is equal to beta 3 0 plus beta 3 2 times the mediator, y2, plus the error term epsilon 3. And again, the error terms, epsilon 2 and epsilon 3, are assumed to be normally distributed with a mean of 0 and with their own individual variances, sigma 2 squared and sigma 3 squared. Now, here are some questions of interest that would be relevant in the context of a mediation model, and they would be answered in terms of one or more models. And so the first question would be, does mediation exist? And so, what does that mean? How would we define that? How would you answer this in terms of one or more statistical models? And so I guess in order to answer that question, we would need to know what do we mean by does mediation exist? And so we're going to look at that in some detail later. If mediation does exist, is it partial mediation or complete mediation? And so if you think about the structure of that initial partial mediation model, the path diagram, how would you answer this question in terms of the model? Finally, let's look at what is called a model that has reciprocal causation. And so here is a path diagram for what looks to be, it's very similar to the multivariate multiple regression model that we looked at previously, but there's one difference. Notice the one-way arrows between y1 and y2. These were not present, they are not present in a standard multivariate multiple regression model. But in this case, we have a one-way arrow from y1 to y2. We also have a one-way arrow from y2 to y1. Now, we also have one-way arrows from each of the variables x1, x2, and x3 to each of y1 and y2. And so based on that, we can conclude that this model is telling us that each of these variables, x1, x2, and x3, and we'll go ahead and call them explanatory variables, is they're impacting each of y1 and y2. Now, we also have these one-way arrows between y1 and y2, and so that tells us that y1 is impacting or predicting y2, and at the same time, y2 is impacting in a predictive fashion y1. So this is much more general than a typical or standard multivariate multiple regression model. The corresponding model is expressed as a system of statistical equations in the following way. So the first response variable y1 is equal to beta 01, the intercept, plus beta 11 times x1, plus beta 21 times x2, plus beta 31 times x3, plus beta 41 times y2, the second response variable, plus the error term epsilon 1. The second response variable y2 is equal to beta 02 plus beta 12 times x1 plus beta 22 times x2 plus beta 32 times x3 plus beta 42 times y1, which is the first response variable, and then plus epsilon 2. And again, the error terms epsilon 1 and epsilon 2 are assumed to be normally distributed with a mean of 0 and their own variances. But here is the interesting thing, okay? Notice that we have the response variables on the left-hand side as we always do, but again, we have those same response variables on the right-hand side as predictor variables in these two equations. And so in the equation for y1, we have y2 as one of the predictors, and in the equation for y2, we have y1 as one of the predictors. And so a question I have you seen this kind of a model before? How would you fit this kind of a model? If we were going to use regression techniques, how would you fit this model? So let's wrap up by talking about complex modeling and flexible testing. So scientific theories are developed, tested, and refined in the context of one or more models of a phenomenon under study. Structural equation modeling allows for very complex models to be fit relatively easy and provides a very flexible hypothesis testing and estimation framework. Many of the models we have looked at in this lecture can be fit using standard regression techniques, but some are more difficult to implement using that approach than others. And there are some that really can't be fit at all with the standard regression techniques. However, all of the models we've looked at can be fit with structural equation modeling software. Even the more complicated models that we have looked at can be fit relatively easily with SEM software. In the coming lectures, we will look at how to fit all of these types of models and some additional models as well, and test hypotheses about them using SEM software. So this is what I wanted to talk about in this lecture video. I'll see you in the next lecture video.